Okay, today we're going to start the growth models chapter. Now remember, this is from the Math and Society book. Now we're going to start with linear growth. Before we do that, we need to talk about a recursive relationship is a formula which relates the next value in a sequence to the previous value. So with linear growth, a recursive relationship is a formula which relates the next value in a sequence to the previous values. If a quantity starts at size p sub 0 and grows by d every time period, then the quantity after n time periods can be determined using either of these relations. We start with the recursive form, which says p sub n is equal to p sub n minus 1 plus d. Keeping in mind that p sub n is the third, fourth, fifth number we're looking for, and p sub n minus 1 would be the previous number. So if we're looking for the fourth one in the sequence, p sub n minus 1 would be the third one. And plus d. D represents the common difference, which is the amount the quantity changes each time n changes by 1. The explicit formula is p sub n equals p sub 0 plus d times n. So in this case, we can find any number in the sequence by taking the starting number p sub 0 and adding d, the difference per time period, times the number of time periods. And if you look at that explicit formula, you may recognize it as a linear equation, y equals mx plus b, which is why we're talking about linear growth. So let's look at a couple of examples of this. The number of houses in a town has been growing according to the recursive rule p sub n equals p sub n plus minus 1 plus 30. With an initial population, p sub 0 equals 200. So we want to calculate P1 and P2. So if P sub 0 is 200, P sub 1 would equal P sub 1 minus 1, or P sub 0, plus 30, which would be 200 plus 30, which would give us 230. To find P sub 2, we simply set P sub 2 equal to P sub 1 plus 30. So P sub 1 we just found is 230 plus 30. So P sub 2 would be 260. Now let's write an explicit formula for this. Remember, going back, our explicit formula is P sub n equals P sub 0 plus d times n. In this case, P sub 0 is 200 and d is 30. So that is our explicit formula. Next, we want to use this formula to predict the number of houses in 10 years. Now, we could go back and use the recursive formula, but we'd have to find P sub 3, P sub 4, P sub 5, P sub 6, P sub 7, P sub 8, P sub 9, and P sub 10 in order to find what it'll be in 10 years. Or we can use this explicit formula we came up with. P sub 10, n is 10, equals 200 plus 30 times n, which is 10. We have 200 plus 300, and we get 500 houses. Okay, now let's look at this from a different viewpoint. When will the number of houses reach 400? Well, we know it's going to be less than 10 years. But in this case, we know what P sub n equals, 400. We know what D equals, 30, and we know what P sub 0 equals 200. We don't know what N equals. So going to our formula, P sub N equals 200 plus 30N, and we know that P sub N is 400. So 400 equals 200 plus 30 times N. Subtracting 200 from both sides, we have 200 equals 30 times N. Then we're going to divide by 30 on both sides. And we get 20 divided by 30, which is, or 200 divided by 30, sorry. 6.667 years. Okay. Let's look at another example of this. The population of elk in a national forest was measured to be 12,000 in 2003. And was measured again to be 15,000 in 2007. Population continues to grow linearly. At this rate, what will the elk population be in 2014? So, my generic explicit formula, P sub N equals P sub 0 plus N times D. Now, here's the problem. I have P sub 0, and I have P sub 4 years from 2003 to 2007. So for N equal 4, I can write this as P sub 4 equals P sub 0, which was 12,000, plus 4 times D. And since I know P sub 4 is 15,000, subtract 12,000, get 3,000 equals 4 times D. Divide by 4, and I get D equals 750. So now I have D, I have P sub 0. I want to know 2014. Well, how many years is that? After that, after 2003, 11. So N equals 11. D equals 750, P sub 0 equals 12. $12,000. So P sub N is what I'm looking for now. P sub 11. 12,000 plus N, which is 11, times D, which is 750. I have 12,000 plus 8,250, which gives me 20,250 elk. So we can use mathematical models to predict future behavior. It's important to keep in mind that very few trends will continue indefinitely. So we must consider what's reasonable for the model. So let's look at another example here. Suppose a 4-year-old boy is currently 39 inches tall, and you're told to expect him to grow 2.5 inches per year. How tall will the boy be in 2 years, 10 years, and 50 years? So what do we know? We know that our initial height is 39 inches. He's growing by 2.5 inches a year. And then I'm going to do this for N equals 2, N equals 10, and N equals 50. So again, P sub N equals P sub 0 plus ND. So P sub 2 equals 39 P sub 0 plus 2 times 2.5. 39 plus 5. 44 inches. That's reasonable. What's that? 3 feet 8 inches tall. And that would be at 6. So yeah, that's possible. How about piece of 10? 39 plus 10 times 2.5 equals 39 plus 25 equals 64 inches. And that would be at 14. We're looking at 5'4". Well, not unusual. And now I've run out of room here, so let's look at n equals 50. How tall is the 50-year-old going to be? So I have p sub 50 equals 39 plus 50 times 2.5, which is 39 plus 125, which is 164 inches. Which is what? "13 feet 8 inches. Somehow that doesn't seem to make sense. So it worked 2 years and 10 years. But when we got to 50, it kind of fell apart. So that's what we have to watch for when we're looking at growth models. And in this case, linear growth. So that covers linear growth.